Côté-Allard, who has developed the BioPoint, and his presentation is on unlocking comprehensive physiological data analysis through multi-sensor wearable technology.
No? Oh, sorry. Okay. Hopefully now you can hear me better. Yeah. So, yeah, so just very rapidly to present myself. My name is Ulysse. I'm from Canada, the French part, Quebec. So that's why I have a bit of a funky accent. And I'm co-founder of Sci-Fi Labs, which developed the Wearable. And I'm also an associate professor here at UIO. And basically, the main interest I have throughout my research from undergraduate up until now is the use of AI on physiological signal, especially in the sphere of healthcare. So basically, just to give you a bit of background of what I've been doing during my PhD, etc., I've been working a lot with muscle activity for prosthetic control. So here you have an image of the myoarmband, which is the main device I was using throughout my PhD. It records 8 channels of electromyography, so EMG, which is basically your muscle activity. And they are recorded at 200 Hertz, which isn't super great because the actual frequency band that you are interested in within EMG will be between around 520 Hertz up until 500 Hertz. So we would at least want a frequency rate of 1,000 Hertz. So there was actually a lot of paper that came out and compared the myoarmband versus more medical grade device and showed that you had much reduced performance using it. And then the question is, why was basically everyone using it? It's more or less, it's the only option that was available at the time, because something like that would cost 200 USD, and we'll see a bit later the type of muscle activity sensor, how much they cost, and stuff like that. It also had an IMU at 50 Hertz, which is super useful for HCI in general. So yeah, I did my PhD basically at first just trying to control, like recognize different gestures based on that, and then we use that as a modality for prosthetic control, for human-computer, human-machine interaction, for in video game rehabilitation, etc., etc. More specifically, what I actually research is how can I leverage the information of multiple people that would have recorded their EMG signal, so that when a new person comes in, we can use less data and still get higher performance. I've also been very interested in how we can adapt the system over time. So physiological signal in general are non-stationary, meaning that if I record, for example, your EMG at day 0 and you come back a few days later, even if you're doing the exact same gesture, the same motion, etc., I will be reading different measurement, be it because the position of the sensor would have been a bit different, difference in pilosity, difference in skin contact with the electrode, just your musculature can change over time, etc., etc. So yeah, I was basically very much interested in how can I try to adapt as the biosignal change without having the person redo some training and things like that. Then I came here to do my postdoc, again in AI with physiological signals. So I worked a lot with photoplethysmography, inertial measurement units, so actigraphy, electrodermal activity. We'll see a bit what they all mean in a tiny bit, but basically we were interested within the sphere of mental health to diagnostic people with bipolar disorder if they're going toward what we call an euthymic state, toward a manic state. Yeah. So we were then using the Empatica E4, which had a PPG at 64 Hertz, which is useful to get the heart rate variability, which was very much an important features related to describing the current mood state of a person with bipolar disorder. Then the actigraphy at 32 Hertz, temperature, skin temperature, and ectodermal activity, so skin conductance at 4 Hertz. And yeah, so basically the point is you get this signal and you have to try to figure out automatically, is the top one from someone going into a manic state, or is it the bottom one? So I don't know if anyone has any guess. This is over 24 hours of time. And yeah, the reason for, I guess, no guess is just those type of signals are very obtuse, right? It's kind of very hard to actually derive some meaningful information from them just manually, and that's why we're using a lot of AI right now to do that. So just for the information, the top one was euthymic, and the patient in the manic state was at the bottom. Another big difficulty when we are working a lot with physiological signal is that there's a huge amount of variability, not only within a subject, but across different subjects. And for applications such as these, one thing that is very important is that you want the system to just work out of the gate. You don't actually want the person to have to go through a full manic episode so that you can get what their baseline manic episode would look like before you're able to predict. So again, that was, even though it might seem a bit different, it was very much related to kind of understanding the general commonality across participants, so that when a new person comes in, just from the get-go, zero-shot learning, we can predict. And this basically, throughout my studies, I've gathered a lot of frustration, let's say, with the device I've been working on, mainly in terms of transparency, accessibility, and synchronization. So from the transparency perspective, it's just the black box algorithm problem. A lot of manufacturers, what they'll do is they have these sensors that aren't necessarily super good. They'll do some processing internally and just give you the result of the processing without ever telling you what's actually happening. And then when you just get heart rate or heart rate variability, you don't have any idea how they were computed. It's very hard to figure out if there's some bias in the data, to figure out if the measurement you're getting, you can actually use them or not, things like that. So that was number one, especially that, like I said, I'm coming a lot from AI, machine learning, and I like to work with the pure raw signal so that I can do my own filtering, feature extraction, etc. So the Empatica E4, for example, the PPG, what they're giving you is the combination of the red and green sensor. They don't really tell you how they put them together. They output that, and then you're supposed to figure out what it exactly means. The other thing is accessibility. So in general, those sensors cost a lot of money. So as an idea, the E4 is $1,600 USD. I know now they release a new version. We'll talk about it later. EMG system, medical grade. There's multiple channels, but basically you're looking at least 20,000 USD to acquire this type of modalities. Which one of the big problems we had during my postdoc is we wanted to have patients out of the hospital and just follow them throughout the years, right? The problem with bipolar patients is that they tend to break them a lot, and then they cost a bit too much to just have them and replace them often. It just also makes it, in general, harder for different labs, especially for a lab that has maybe less funding to get access to these, so you can do a less type of experiment. It makes it harder to scale the project you're wanting to do. And there's also the accessing of the data itself. So often it comes with subscription, so the Empatica E4, the new version, I think they're selling it for like 600 USD, something like that. But then you have to subscribe for 3 years for 5,200 USD on top of that. So a lot of recurring thing. Cloud service, which, especially within the context of things like the GDPR, make it very hard to actually deploy and use these devices, because then you have to think a lot about data privacy. The actual manufacturer of the device has to be able to certify that the data will be pseudonymized sufficiently. It just adds a lot of complexity in the research. And then just, in general, getting access, if it's possible, for the raw data, download, streaming, etc. The last thing is synchronization. So, in general, to have a holistic experiment, we want to often be able to work with multiple sensors at the same time. All of these sensors often are from different manufacturers, which just makes it hard to synchronize, especially when we're talking about millisecond or sub-millisecond synchronization level. At the second level, then it's relatively easy. Then incompatibility. And then clock drift, which is something that beyond any type of implementation you're going to have, any device that you're using will have an internal clock that will tell it basically what time it is. And all its behavior will be driven by that clock. Meaning that if you're recording something at 1 Hertz, it will be based in its internal clock how long it has been since the last time it recorded. After a second, it does that. So this is a perfect clock. So as the real time passes, the local time passes 1 to 1. And of course, we live in the real world. So in reality, you have the clocks that will have some skew in them. They might have some offset together. And then you also have some amount of drift, meaning that the measurement that you're getting from any type of device will be different than any other device. Even if you would start them at the exact same time perfectly, over time, if you're doing experiment over 24 hours, 48, 4 weeks, etc., even a few minutes, they will start to drift. And this problem compounds more and more as you add more sensors to it. To give you an idea of the scale of the problem-ish, the typical wearable clock precision ranges from 20 to 50 ppm, so part per million. It basically means that for every million second, your device will have like plus minus 50 seconds. So for a full day at 50 ppm, you're looking at a drift of 4.32 seconds. For some experiment, it doesn't matter. For other, when you're looking at physiological signal and you want to actually have millisecond accuracy, this is like you're completely missing everything. So this brings us to kind of the BioPoint, which we try to address as much as possible all these grievances, because first and foremost, we are both researchers, me and my co-founder, and we just want to be able, it all started because we wanted to use a device that works for what we wanted. And then we realized kind of rapidly that if we want to use that device, we need to have a certain amount of scale, because otherwise the price point would be too high, right? So basically BioPoint is, it's still in prototype phase, but this is it. And then we're getting electromyography, skin conductance, electrocardiography, skin temperature actigraphy, and photoplethysmography at the same time continuously in streaming. So just to go a bit over all 3 points and how we try as much as possible to address them is that you can get direct access to the raw data, both in streaming in real time, and there's also onboard memory, so you can do a fine experiment and download it over either the Bluetooth, or you can plug a USB-C cable and upload it. We're targeting below €499 per device, and there's, of course, no subscription fee for the data access. There's no upload to cloud or anything like that, which, again, we're using it in our research, and it would just make it a lot more complicated. And all the sensors operate on the same hardware platform, meaning they will all be able to share the same clock, meaning that we're not pretending that the clock we have or made is perfect, but they all will drift together, right? So even after 2, 3, 4, 5 days, they will all be perfectly synchronized within themselves. We're also using a high precision clock, so we're at 5 ppm, so we are reducing to 0.432 seconds per day of the, on average, drift. And we're also integrating with lab streaming layer. If some of you know about it, it's basically a open source software that allows you to connect different devices from different manufacturers, and then it attempts to do synchronization on the computer side or the server side once it receives the data. So here, what I thought is just to maybe go a bit rapidly into the different type of sensor that we have, what they actually mean. So electromyography is basically just when you're trying to move your skeletal muscle, your brain sends some type of signal that goes through the motor neuron and then excite your muscle fiber, which is a whole electrical process. And what we're able to do is measure this electrical signal. So the size of it is around 1 to the minus e to the minus 6, so it's microvolts level. And it's used for movement disorder, biofeedback, training, optimization in athletes, synchronization with muscle movement also. The other one is electrocardiography. So this is very well known, but heart rate variability. It can help detect different conditions. Again, biofeedback, and that's something that's emerging more and more within mental health too, to actually ask the person to try to guess their heart rate variability, and then you can have them basically tell them if they're wrong or right, and this is just a way for them to be more conscious of what's happening if they are feeling stress, things like that. And the other fun thing is that it can be used to derive indirect metric. So we'll see it a bit more later, but for example, respiration rate, which is, those are all estimation always, but basically you can more or less look at the amplitude here, and this slow drift is very much related to respiration, because when your lungs fill up with air, it will come and change where the electrode is in respect to the heart, and then you can have a bit of that measurement going through. The next one is skin conductance, ectodermal activity. This was, as you can see, you're having it go a bit faster than real time. This was during the night, taken on a forum. So this is indicative of what we would call an EDA storm. The way we're measuring it is we basically send a very, very small signal through the skin and measure a known signal, and then we measure we measure that signal at another electrode, meaning that the resistance of the skin will affect the measurement we get, and basically your sympathetic nervous system which control sudation, when it's activated or when it's suppressed, will change the resistance that we're reading, which is basically what you were seeing. So the EDA storm that you've seen is very much associated with deep sleep. So it can be used as an indicator of emotional state, biofeedback again, monitor pain, because people that are in pain tend to have reaction within the EDA that is measurable, and also for sleep monitoring. Skin temperature very rapidly, again, circadian rhythm, sleep monitoring. This is taken over, I think, 10 or 12 hours. Sleep monitoring, health status, biofeedback, etc. And finally, maybe one of the most important, the photoplethysmography. The way it works, it's just you send a small light through the skin, and you have two types of PPG. The one you'll see at the hospital where they put on the finger. Basically, you have the light that goes here, and you have some photosensitive sensor here. So it's going through the finger, and we're measuring the amount of light that goes through. And the idea is basically when your heart is beating, it creates a pulse of blood going through and back and through and back, and so the density of the blood change, and so the amount of light that is absorbed also change. And this is what you're seeing here. This is a type of PPG that is called bireflectance, so instead of going through the finger, when you're putting it on the forearm or the biceps or torso, etc., some amount of light will be reflected back, and this is what we're measuring, is how much light change. This type of sensor is what you'll have in every single smartwatch. That's what you'll have in every single smart ring. They will tend to have either just the green, or some of them will also have infrared and red. And the reason for that is that they're super useful to make measurement of heart rate variability on a single point. They can be used for blood pressure estimation. This is a bit harder, I'll tell you a bit after. And also for oxygen saturation, SpO2. So the idea, and that's why you need red and infrared for that type of measurement, is that the amount of absorption for hemoglobin when it's filled with oxygen and it's not, is basically inverted when you add the red and when you add the infrared. So you can basically measure both the absorption from the red side and infrared. You cancel like the DC and things like that. And you can get an approximation of how much oxygen there is in the blood. Finally, inertial measurement unit. That's a super fun and useful sensor. This is also available in every single smartwatch, smart ring, etc. Probably in every single sensor that you'll get. You might not have an inertial measurement unit. You might just have actigraphy, accelerometers. But basically, it's useful to evaluate movement. So what you're seeing here is me walking. As you can see, each peak is basically a step. So that's how you can do step count on your smartwatch, or you just do, it's quite easy. And then you can do sleep studies, see when the person stops moving, start moving. We've worked a lot with it with bipolar disorder. So actigraphy is actually a very, very good indication of the actual state of the person. When I started working with it, I was imagining that the manic patient would just move all the time, whereas rhythmic wouldn't. The reality is a bit more complicated. What we're looking at for actigraphy in bipolar disorder is more the complexity of the signal. So someone in a manic state will have tendency to have more complex movements, so start, stop, etc., and not so much move non-stop. And it can be used for the orientation of the limbs. So this, in conjunction with, for example, EMG, you can start doing some very cool gesture for human-robot interaction, where you can understand where the person is. So, for example, this could do a different gesture than this, even though from an EMG side, it's the same, more or less the same. And this is actually the very big thing. if it's synchronized well, and then we're talking sub-millisecond, you can actually use it to alleviate a lot of movement artifact. So more or less, all this sensor, PPG in particular, but EDA, ECG, EMG, they all rely on good connection and constant connection with the skin. So as soon as you're doing some movement, some vibration, right, you're going to change the point of reading compared to the point of what you're reading, which will affect the signal. And then when you have access to that type of thing where you actually can see precisely when the person is moving, you can do two things. You can either do some filtering, so try to remove the influence of that signal, or if it's too intense, you can just detect that this period of time too much movement and just reject automatically the signal. Yeah, so like I said, the BioPoint is, for those who have worked a bit with microelectronic, we're extremely, extremely packed. So it was, to the best of my knowledge, there's nothing that exists right now that has all of these sensors together. I won't lie, it was very technically challenging to get those signals and not affect each other, because we're talking about microvolt and things like that. Just generally speaking, again, if you have any question, don't hesitate. The way it works mostly is that you have the charging USB-C port. It's also how you're going to measure the ECG. So for the ECG itself, you cannot make it, as far as I know, and I've researched that, you cannot have any ECG measurement from a single point. The reason for it is more or less you want to have 2 points that cross the heart so that you can have an actual difference of measurement. So in my instance, and I can show you a bit later the type of recording, and just to be clear, all the recording I've shown was directly the raw data. But yeah, in my instance, I have the ECG here, and then I have an electrode here, and then I can measure continuously through it. It is also possible to get it without that by using an electrode on the top. Something like an Apple Watch will also have that type of thing with the crown button where when you touch. That way you basically have a circuit that go 1 point here, all the way here. And that's equivalent to a V1, if I remember correctly. Wait, I fully forgot where my thing is. Okay, anyway. Yeah, so just for the spec a bit of the actual frequency rate and things like that, this is something that is very much possible to be changed. Right now, what we've done is what we think would be the most, that would make the most sense. Frequency rate will always be a balancing act between battery autonomy, the amount of memory that it will take, and the bandwidth for transmitting it. But basically, we have the PPG at 50 Hertz. We add it at 200 Hertz without problem. The EDA, the signal itself that we send, it's at, we can do it at DC, and that allows us to record at the same time EMG and ECG. We can also have an AC signal, which in general provide faster contact with the skin. EMG is at 2000 Hertz, ECG at 500 Hertz, skin temperature at 1, IMU 50 Hertz, and like I said, Bluetooth to energy, real time, etc., etc. Okay. So just to give a bit of an example of why you would want to have all of these sensors together, I want to go a bit into the pulse wave velocity. So basically, when your heart is pumping, what happens is that it's very annoying. Okay, no. Well, anyway, when the heart is pumping, you have this ECG signal, and you see this big peak here. It's called the R peak. There's the QRS signal that is a bit around it. And that's when the ventricle basically contract and send the oxygenated blood through the aorta, which create a pulse that propagate throughout the body. And then you have something like a PPG that would be on your forearm or on your finger, right? So there's a certain distance between where your heart is and where the PPG is, and that distance means that it will take a certain amount of time for your pulse wave to travel all the way to where your finger is. And meaning that when you have both, you can actually calculate the pulse wave velocity. And this is directly related to the arterial stiffness, which is a very, very big indicator of risk of stroke, for example, which meaning that it's very useful to have. It's also a very good indicator to help you compute an estimation of blood pressure in a continuous manner without any cough. So, yeah, the idea is you use the ECG to pinpoint when the heart starts the contraction, and you use a PPG to actually capture when the blood arrives at the point of measurement, which, if the signals are well synchronized, then you can get what we call the pulse transit time, and then you can get the pulse wave velocity by dividing, well, by having the distance divided by the pulse transit time. I can maybe show some example of okay. If you just give me a tiny second, I'll change the way I'm showing everything. Because I just want to give a bit of an example of how you can get the data, etc. Okay, I won't be able to do that because apparently I went full blue screen of death on my computer. So I'll be right back. Yeah, oh no, my computer just restarted fully. No, I'll just restart in a second. But yeah, so if anyone has any question, you're very welcome for it right now. Yes? Yeah. Yeah.
Sorry, I forgot if you mentioned it. Is there anything?
Yes, so we are actually also working on what we call the BioPoint. So it has all the same sensor of the BioPoint, but it has 8-channel EMG at 1,500 Hertz. Yeah, and I can show a demonstration, but if you, I'll have an image. So this is still kind of prototype. I have the image of more the robust final version. But yeah. And the idea of having it more in a rectilinear fashion is that then you can strap it also, for example, on the stomach, back, around the hand, and etc. So we are still a bit working on the attachment point and things like that, but okay, I'm coming back. Sorry about this time.
Could I ask a question?
Yeah. Yeah.
Or no, you go ahead. If it's gonna
No, you can ask.
I guess I know I've heard that like one of the issues with buying sensors from companies is that sometimes these companies just stop all of a sudden.
Yeah.
And I wanted to know if somebody was to invest in your product, like what kind of support do they have, and then how long do you expect it to last? Like, Is there any guarantee that it wouldn't just stop, for example? Because I know with the Myo armband, I think that stopped, or there's various other companies that have just gone under or disappeared because people buy them up.
Yeah.
Are you going to resist like big corporations trying to buy you, or how is that going to work?
Yeah, it's, well, the reality of it is that our plan is very much to grow and to work right, but the reality of it is that we're in a startup phase. We're in the valley of death, that is called. So we have the start of the product. Everything seems to be working well. We're starting to have actual hospital using them, university, etc. So everything works very well, but if I'm fully honest, I can't give a guarantee that we won't collapse at some point. That being said, so far, it's every sign show that it's going very, very well, let's say.
You just got like the assistant professorship,
Yeah.
so you're balancing both these, like, because this is part of your work, is there, and that's more of like a job, it's like secure job, so is this, maybe that's one way you can kind of have some kind of guarantee, because it is very relevant to your research as well, right?
Yeah, it is, and what it allows us to do, of course, yeah, if you have also questions about entrepreneurship from academia to and working with both, I'm also very happy. I'm not pretending I'm an expert, but that's something I've been dealing with for a while. So we have to go through ethical committee, of course, to be fully transparent into what the company does, what I do as research, and make sure whenever the two can overlap to declare it. But we do see a lot of synergy that come from being both in the academic side and industrial side. And like I said, the main reason why we started it is that we were just very frustrated with what was for the research we wanted to do, and we wanted to make it better, right? So at the core of it is that we're very interested in research, etc. For your initial question, I would say one of the big advantages with the system we're doing is that we provide the raw data. We don't have cloud service, we don't have subscription, things like that, meaning that even if we go under, your device still works, right? It doesn't stop working, you can still record, etc., etc. The goal is very much not to go under. So I just wanted, speaking of which, I don't know if people fancy a bit of coding, but I just wanted to show a bit rapidly one of the way you can get in contact with the BioPoint. So just, okay, that thing. So this is just an example, very rapidly, of all the signal together. It's replacing, etc. You have the ECG, which is the red one on top, and also the PPG. One thing I want to kind of have you notice is if I start moving like crazy, especially on the PPG side, for example, infrared, right? What it starts measuring is actually more my movement than actually my heart rate. So that's why things like acceleration is very, very useful. The other thing is that for PPG specifically, another big advantage of having blue, green, red, infrared, one of the things they do is basically the blue one will penetrate the least inside the skin, the infrared one will penetrate the most. If you have participant or patient with different skin color, one thing that does is affect a lot the depth of penetration of the different signal. So one, having different color like that can help compensate. The other thing is that we're allowing you in real time to change the amount of intensity for all the lights, and we're also allowing you to change in real time the amount of sensitivity. So we're working on kind of a real-time optimization for wherever you put the BioPoint and also wherever, on whomever you put it. So this is one of our big focus right now. So just to show very rapidly, one of the way you can interact with it, it's not the only one, but it's, I think, something that is kind of very, very useful and cool, is that we've made what we call a command line tool. So it's basically, that file is a sci-fi bridge.x. You can have it for Linux, you can have it for Mac, you can have it in principle for Android, etc. And what it does is it's allow you to just call from any programming language, as long as they support sub-process. So in principle, you can talk to it from R, you can talk to it from MATLAB, Python, C#, C++, C, literally any programming language. You just open the sub-process, and then you're good to go. So here we would try to connect to the device. So we're just like trying to make sure, is the device on? Can I connect to it? And then as soon as you do, it says, okay, everything is good. And then here, I'm sorry, the resolution isn't super good. But here it's basically, you tell it which channel to open. So in our case, we're opening the EDA and PPG. You can decide to open all of them. You can decide to just have one. You can decide to enable the filter on board or not, so to get even more the raw data. You send the command then to start the acquisition, and then it just records. And then you can decide to send the command to stop the acquisition, download everything, etc., etc. So it's not bound to any specific software that we would be developing. You just can have the scripts you want and control it. And it's the same for the BioPoint. 5 minutes, yeah, okay, so I'll just wrap up. I'll just wrap up very rapidly with the BioPoint, which we've been working on. Like I said, it has all the same sensor as the BioPoint, which is actually, I think, very cool, because then you can do a lot more type of experiment where you can measure both things like stress, heart rate variability, etc., in situation where the person is controlling, playing piano, things like that, and you can actually see better the different movement. It's cadence at 1,500 hertz, so we're well above the 1,000 hertz to get all the frequency information. There is, because we're using Bluetooth to energy, there is kind of a day before sending everything. We're at 7.6 milliseconds. As a comparison, the MIO is at 5 milliseconds, and the DELSIS is at 14 milliseconds. So generally speaking, as you don't want to be above kind of 50 milliseconds for gesture recognition, max. So this is well below. For some application, maybe you would need even smaller than that. One thing we're working on is to have the possibility to connect a USB cable directly to your computer to reduce that. The thing we need to do for that is we have to make sure we don't send any power through that cable, so we're looking at optocoupler and things like that. But yeah, it's in the work, and then just a very quick demonstration where we're using it to play a game or control a quadcopter. This is like from Linux and Unity, C#. This was in Windows with Rust and things like that. So yeah, thank you very, very much.
Thank you so much, Ulysse. We now have 4 minutes for questions. So if anyone would like to start here, I'll also just open up the YouTube chat. Perfect. Here,
Yes.
Marc. Fellow Québécois.
Music en français.
En français? Okay.
In English for now. Music applications, like music applications for interfacing with like softwares like Pure Data or MaxMSP or.
This is something I have a bit knowledge on. That being said, RITMO got some BioPoint and things like that, and we're very much in the time where we're doing a lot of collaboration. So when we're saying we don't sell the sensor kind of to anyone, we want to have collaboration with the people. So yeah, this is something we're very interested in. This fall, we're actually partnering with a course that Dana is also giving with students from the musicology department.
Yeah.
So we are very excited to see the type of thing they'll do and also understand the specific need in music for it.
Very cool.
Yes, and actually 2 of the students are currently streaming this up onto
okay,
YouTube.
super.
So Jack and Amin, that's why I had you guys sitting here to watch this presentation, because this is one of their potential projects that they could participate in. Any other questions?
Thank you for the presentation. It's really cool to see so many sensors in such a small box.
Thank you.
I know that some wearable devices don't have the same level of precision depending on where you put them on the body. Different wearable devices have different precision levels depending on where you put them. Like I know you show for the arm.
Yeah.
I'm wondering, like, for other type of application, if you put it somewhere else.
Yes, so I think I have it. We also have, like, I hope I brought it. Sorry about that. Okay, anyway, we have like strap more like a meter long, so you can go torso, etc. We'll also have patch, double-sided patch with medical grade tape, so you can actually place it anywhere you want.
But would you lose like precision in one of the area if you decide to put it on the leg, for example, if you're more interested in walking, or if
yeah, so for example, with the EDA, the best position to put it is on the finger, right? So as soon as you go on the forearm, or I don't know, the torso, things like that, you'll have less precision, well, you'll have less good contact with the EDA. That's basically the only sensor with that. There's also the PPG with the different depth and width of skin, etc. But that's why we'll also have the possibility to have higher intensity for the light, etc. One thing I'm doing is trying it on my dog, who's like very furry and very black hair and stuff like that. So I'm trying to cover as much as possible.
Thank you.
All right, thank you for a great presentation. It's great that there's more hardware coming.
Thank you.
To pick from. I might have missed this, but so if I understood correctly, you only use the Myo armband style thing for the EMG, right? Have you
in my PhD?
in this kit?
No, in this. Here.
Yeah, that one, right?
Yeah. So that's the bio armband. So we've developed that too.
Right.
Yeah.
Have you, because that's just like an armband setup, have you any plans or already tried individual ones? So more to be able to target more precise muscles, or the armband styles?
Yeah, so the idea would be that the BioPoint, you'll be able to connect multiple. So we're also working on a base station. So hopefully you'll get to connect 12, 16, a bit like the Delsys
right.
with RU to do that. And
that would be great, yeah.
What's great is that you're both here in Oslo, so you can collaborate with him for your project, which is very related. Are there any final questions for the audience here? If not, we have a quick one online.
Yeah.
So Andriy Smikovsky has asked, could you elaborate on how, okay, so thanks for your interesting presentation. I'm curious about your device's applications. You discussed its role in detecting mood variations as well as detecting euthymic and manic states in patients. Could you elaborate on how you established the ground truth about the nature of the data and its relation to different moods?
Yeah. For my research during my postdoc, we didn't use the BioPoint full disclosure. We were using the Empatica E4. The way it worked is basically the patients were hospitalized. They were assessed by psychiatrists to determine they were in a manic state. And then they were asked for consent if the psychiatrist thought they were in position to consent for it, and then they wore the empathic IFO for 24 hours. Just before their dismissal from the hospital, once they were diagnosed as euthymic, then they were asked the same thing if they wanted or not. So then for some of them, we have recording of them both in euthymic and manic state. A lot of them, we just have one of them. Yeah, and then we have a journal paper I'm happy to link with all the
I
persons.
linked your SIFI Labs website into the chat so that
Okay.
they could contact you.
Yeah.
So thank you so much, Ulysse. That begins this next break. Another round of applause. Thank you.